On Friday, August 21st, 2026, the ground started twitching again in a remote stretch of California desert 100 miles northeast of Bakersfield. 7 earthquakes rattled the Coso volcanic field by that afternoon, the strongest, a magnitude 3.4. On its own, that's a minor, forgettable news story. A handful of small tremors in the middle of nowhere. But this is not an isolated event. It's the third earthquake swarm to strike this exact same corner of the California desert in roughly 2 months, sitting directly on top of a magma chamber, right next to a fault capable of producing one of the largest earthquakes the state has ever seen. Scientists monitoring the region have a name for what's driving this cluster of activity, and it traces directly back to an earthquake that happened 7 years ago. But the frequency of what's happening right now, 3 separate swarms in the span of about 8 weeks, is genuinely unusual even by the standards of one of the most seismically active patches of ground in the United States. By the end of this video, you'll understand exactly what's been shaking this stretch of desert all summer, why it's happening in a location that combines 2 of the most serious geological hazards in California into a single spot on the map, and what seismologists are actually watching for to determine whether this pattern means anything more than what it appears to be on the surface. According to the U.S. Geological Survey, 7 earthquakes struck the Coso volcanic field near Coso Junction on Friday, August 21st, with the strongest registering magnitude 3.4 at 10:26 in the morning Pacific time. The Coso volcanic field itself isn't a single peak or crater. It's a sprawling, roughly 150 square mile cluster of volcanic features, sitting on top of a large underground zone of magma, and dotted with dozens of vents, domes, active geothermal fields, fumaroles, and natural hot springs. Because the region sits directly above an active magma system, any burst of earthquake activity there automatically draws close attention from the California Volcano Observatory, which monitors the area specifically for signs that seismic unrest might be linked to volcanic processes rather than ordinary tectonic stress. In this case, the observatory confirmed there's no ground deformation or other indicator suggesting an eruption is imminent. The volcano alert level remains at normal, and the aviation color code, a separate warning system used specifically to flag ash hazards to aircraft, remains at green, the lowest level on that scale. Coso's most recent actual eruption took place tens of thousands of years ago, and while the field remains geologically active in the sense that matters to volcanologists, an eruption in the near term is considered unlikely. Taken entirely on its own, in isolation, this week's swarm would barely register as news. Small earthquake clusters happen constantly across California, and this region in particular has a long, well-documented history of exactly this kind of activity. What makes this specific event worth a closer look is what came immediately before it. This week's Coso volcanic field activity isn't the first swarm to hit this general stretch of the eastern California desert this summer. It's the third. Seismic monitoring groups tracking the region had already logged a swarm designated S2260713.1 on July 13, 2026, striking the same broader area just north of the Garlock Fault, in the immediate vicinity of the 2019 Ridgecrest earthquake rupture zone. That July event was itself explicitly logged as the second swarm of 2026 in this specific stretch of the eastern California shear zone, meaning an earlier swarm had already struck the same general region sometime before it, earlier in the year. Put those 3 events together, and you get exactly the pattern behind this video's title. 3 separate earthquake swarms, in the same tightly bounded corner of desert within roughly a 2-month window. To put that frequency in perspective, seismic researchers cataloging swarm activity in this exact area found only 2 distinct swarms recorded there across the entire 18-year stretch between 2000 and 2018, one in 2009 and one in 2016. Since the 2019 Ridgecrest earthquake sequence, that pace has accelerated dramatically. Researchers have identified 6 separate swarms in this same area in the years since 2019, including 2 in 2019 itself, 2 more in 2025, and now what appears to be a 3rd distinct cluster in 2026 alone. A region that used to produce a notable swarm roughly once a decade is now producing multiple swarms within a single summer. It's also worth being precise about what actually counts as a swarm in the seismological sense, because the term gets used loosely in casual conversation, but carries a specific technical meaning that matters for understanding why researchers track these events so carefully. Unlike a standard earthquake sequence, which begins with one dominant main shock followed by a gradually decaying series of smaller aftershocks, a true swarm has no single dominant event at all. Instead, it's a cluster of many small to moderate earthquakes occurring in rapid succession within a short window of time and a tightly confined geographic area, with energy released in scattered increments, rather than concentrated in one large rupture. Seismologists sometimes compare the difference to the snap of a single dry twig versus a bag of popcorn popping. one large, sharp release of energy compared to many smaller pops scattered across a short stretch of time. That distinction is why swarms get analyzed differently than ordinary aftershock sequences. Without a clear main shock anchoring the pattern, researchers have to rely on the cumulative frequency, spatial clustering, and depth of the individual quakes within a swarm to determine what's actually driving it. To understand why this specific patch of desert has become such a persistent source of earthquake swarms, you have to go back to July 2019, when a magnitude 6.44 shock and a magnitude 7.1 main shock struck near Ridgecrest, California, the largest earthquake to hit Southern California in 2 decades. That sequence didn't just shake the immediate area around Ridgecrest, it fundamentally altered the underlying stress field across a huge surrounding region, triggering earthquake swarms in Panamint Valley along the Garlock Fault and northwest of the Coso geothermal field, collectively producing thousands of additional smaller earthquakes at considerable distance from the original rupture zone. Researchers who studied the aftermath found that the overwhelming majority of these triggered earthquakes occurred specifically in areas where the Ridgecrest main shock had added measurable stress to local faults, effectively nudging them closer to their own individual breaking points, whether or not the underlying fault ever actually ruptured as a result. This entire region sits within something that geologists call the Eastern California Shear Zone, a broad, diffuse zone of deformation that runs along the southern extension of the Walker Lane, together accommodating somewhere between 15 and 25% of the total motion occurring between the Pacific Plate and the North American Plate. That's a genuinely significant share of one of the most consequential tectonic boundaries on the planet, distributed across a wide network of smaller interconnected faults, rather than concentrated on a single well-known fault line, the way most people picture California's earthquake risk seismologists. Studying the persistent swarm activity in this specific corner of the shear zone describe it as part of an ongoing, long-term crustal adjustment process, the surrounding rock still working through the redistributed stress the 2019 sequence left behind, years after the original earthquake itself has faded from headlines. Historically, faults within the Walker Lane and its continuation south into the Eastern California shear zone have hosted several of California's largest earthquakes on record, giving this broader region a well-established pedigree for major seismic events even before Ridgecrest. The 1872 Owens Valley earthquake, located roughly 50 miles northwest of where the Ridgecrest sequence eventually struck, is estimated to have reached somewhere between magnitude 7.8 and 7.9, making it one of the largest earthquakes in California's modern historical record. That event predates modern seismic instrumentation, so its exact magnitude carries some uncertainty, but geologists studying the region point to it as clear evidence that this stretch of desert has hosted genuinely massive ruptures before, independent of anything connected to the 2019 sequence. The broader takeaway from that history is that the Eastern California shear zone isn't some minor, secondary hazard sitting in the shadow of California's more famous faults. It's a legitimately major piece of the state's overall earthquake risk. Picture one that simply doesn't get the same public attention as the San Andreas because it runs through comparatively sparse desert rather than directly beneath major population centers. Here's where this story moves from interesting geological footnote to something considerably more consequential, because this recurring swarm activity is happening directly adjacent to one of the most dangerous and most historically quiet fault systems in California. The Garlock Fault runs roughly 250 kilometers, or about 155 miles, east to west, marking the northern boundary of the Mojave Desert and connecting the southern end of the Sierra Nevada to the western edge of the Basin and Range Province. Unlike the San Andreas, which slides in a right lateral direction, the Garlock is a left lateral strike slip fault. And for essentially all of recorded California history before 2019, it had no documented history of significant movement or of producing strong earthquakes on its own. That changed with Ridgecrest. A team of researchers from Caltech and NASA's Jet Propulsion Laboratory, publishing their findings in the journal Science, confirmed that a section of the Garlock Fault actually slipped as a direct result of stress transferred from the 2019 Ridgecrest sequence, the first time that specific movement had been documented on this fault in the modern seismic record. Subsequent USGS analysis found that the Ridgecrest earthquakes increased stress on the Garlock Fault by roughly 30%, a genuinely significant jump for a fault of this size and potential. To be clear about what the science can and can't tell us here, researchers have been careful to note that whether this stress increase actually triggers a major Garlock rupture within days, years, or decades, or ever, remains genuinely unknown. The 30% stress increase measured after Ridgecrest is real and scientifically significant, but it doesn't function as a countdown clock. What it does mean is that the fault is measurably closer to failure than it was before 2019, and that every subsequent swarm of smaller earthquakes in the same general area gets monitored at least in part, through the lens of whether it might represent another incremental step in that same ongoing stress transfer process. There's real historical precedent for exactly this kind of delayed trigger scenario, and it's part of why seismologists take the Garlock. Stress increase seriously even without a specific timeline attached to it. In 1992, a magnitude 7.3 earthquake struck near the town of Landers in the Mojave Desert, another event within this same broader Eastern California shear zone system. Researchers studying that earthquake's aftermath identified a similar pattern of stress transfer onto a neighboring fault system. And 7 years later, in 1999, a magnitude 7.1 earthquake struck near Hector Mine, on a fault that seismologists had specifically flagged as carrying elevated stress following the Landers event. That 7-year gap between the original stress transferring earthquake and the subsequent triggered rupture is precisely the kind of delayed timeline that makes ongoing monitoring of the Garlock fault, now similarly loaded with stress from an earthquake that happened 7 years ago, feel less like abstract academic concern and more like a genuinely open, live question. Layered directly on top of that fault hazard is the second geological complication making this particular stretch of desert worth watching closely: the fact that a genuinely active volcanic system sits right in the middle of it. The Coso volcanic field isn't dormant in the sense that many people picture when they think of an inactive volcano. It sits above a real mapped zone of underground magma, and that magma system is directly responsible for the extensive geothermal activity found across the area. Active fumaroles, hot springs, and a geothermal energy field that's been commercially developed for decades, specifically because of the reliable underground heat this magma system provides. That combination, real. Magma at depth plus a location sitting directly within one of California's most seismically active shear zones is exactly why the California Volcano Observatory treats every swarm in this specific area with a slightly different level of scrutiny than an equivalent swarm happening somewhere without an underlying volcanic system. The key distinguishing question scientists ask during any Coso area swarm is whether the activity is tectonic, ordinary fault movement responding to regional stress, the same basic mechanism producing earthquakes anywhere else in California, or whether it's volcanic in origin, meaning it's connected to the movement of magma or geothermal fluids beneath the surface, which would carry entirely different implications. The tool that lets scientists tell the difference is ground deformation monitoring. Magma moving beneath the surface physically pushes and swells the ground above it in ways that satellite and GPS-based monitoring can detect, even when the actual movement is too subtle to feel. When a previous swarm struck the southern margin of the Coso volcanic field back in July 2025, triggered by a magnitude 5.4 earthquake that was itself an aftershock of a nearby M7.1 event, the USGS explicitly confirmed that swarm was tectonic rather than volcanic in nature, specifically because no deformation indicative of magma movement had been detected. That same confirmation, no ground deformation, no volcanic signature, has now been repeated for this week's swarm as well. That repeated tectonic classification matters because it tells researchers something specific about what's actually driving the activity. Rather than magma pushing upward and cracking the overlying rock as it moves, these swarms are being generated by ordinary fault slip on the network of smaller faults that happen to run through and around the volcanic field, responding to the same regional stress changes affecting the broader Eastern California shear zone. The volcanic field's magma system is essentially a passive bystander sitting geographically in the middle of an active tectonic zone, rather than an active participant driving the earthquakes themselves. That distinction is reassuring in one specific sense, since it rules out an imminent eruption as the explanation for any of this summer's activity, but it doesn't change the underlying tectonic hazard picture at all, since the same regional stress field responsible for these swarms is the same stress field that's been loading the neighboring Garlock fault since 2019. Here's the central question this entire story revolves around, and it's worth answering with real numbers rather than gut instinct. Yes, by the historical record for this specific location, 3 swarms within roughly 2 months represents a genuinely elevated pace, even accounting for how seismically active this corner of California has always been. Remember the historical baseline. Only 2 documented swarms in this exact area across 18 years between 2000 and 2018. Compare that to what's happened just since the 2019 Ridgecrest sequence. 6 separate swarms across 7 years, with the pace apparently accelerating further into 2026, where this region may now have already produced 3 distinct swarms within a single summer alone. Seismologists studying this trend describe it as strong supporting, evidence that the surrounding crust is still actively responding to the massive stress redistribution the 2019 Ridgecrest sequence set in motion. In other words, the Earth in this specific area hasn't yet finished settling into whatever new equilibrium it's working toward following that earthquake 7 years later. That said, it's important to be precise about what not normal actually means in this context, because there's a meaningful difference between statistically elevated relative to this location's own recent history and a warning sign of an imminent, larger earthquake. Seismologists have been consistent across nearly every individual swarm covered in the reporting on this region in stressing that earthquake swarms, even frequent ones, are not reliable precursors to larger earthquakes. The scientific consensus on swarm behavior generally holds that most swarms represent the gradual incremental release of accumulated stress along a network of small, often unmapped faults, rather than the kind of stress buildup that precedes a single, larger main shock. That's a genuinely different mechanism than the classic foreshock, main shock, aftershock pattern most people associate with earthquakes, where a period of smaller shocks builds directly toward one dominant, much larger event. So if elevated swarm frequency alone doesn't automatically signal an approaching disaster, what specifically are scientists watching for? That would change that assessment. Two things stand out clearly from how researchers have discussed this region. The first is ground deformation. As long as GPS and satellite monitoring across the coastal volcanic field continues showing no meaningful surface deformation, scientists have a strong, direct basis for ruling out volcanic unrest as the driver behind any given swarm, regardless of how many small earthquakes are involved. A genuine change on that front, actual measured uplift or ground movement consistent with magma migration, would represent a categorically different and more serious situation than what's been observed through any of this year's 3 swarms so far. The second is the magnitude and behavior of any individual earthquake within these swarms relative to the Garlock Fault specifically. Because researchers have already confirmed a measurable, quantified stress increase on that fault following Ridgecrest, any future swarm activity that shows earthquakes migrating directly onto mapped sections of the Garlock itself, rather than remaining on the smaller surrounding faults, where this summer's activity has so far been concentrated, would represent a meaningfully different signal worth far closer attention. So far, based on available reporting, this summer's 3 swarms have remained centered on smaller faults within the broader Eastern California shear zone and COSO area, rather than showing direct migration onto the Garlock's own mapped fault trace. As of this week, the California Volcano Observatory continues monitoring the COSO volcanic field following Friday's 7 earthquake swarm, with a volcano alert, level holding at normal and no deformation detected. The USGS continues cataloging individual earthquakes within the broader Eastern California shear zone as part of its ongoing regional monitoring. And seismic researchers tracking swarm frequency in this specific area consider the current pattern consistent with the longer-term trend of elevated post-Ridgecrest activity documented since 2019, rather than representing a sudden, unexplained departure from that trend. Separately, ongoing research into the Garlock Fault's stress state continues, building on the original Caltech and JPL findings that first identified the fault's post-Ridgecrest slip and the associated 30% stress increase. That research remains active precisely because the fundamental question it's trying to answer, whether and when that added stress might eventually translate into a major Garlock rupture, doesn't have a definitive answer yet, and likely won't for some time. Scientists continue treating every subsequent swarm in this broader region as another data point worth logging into that longer-running investigation, even when, as with this week's event, the individual swarm itself remains modest in scale and squarely within the range of activity this specific patch of desert has been producing with increasing frequency since 2019. What makes the story worth following isn't any single one of these 3 swarms in isolation. A handful of magnitude 3 and 4 earthquakes in a remote stretch of desert wouldn't normally warrant sustained attention on its own. What makes it worth following is the pattern those 3 swarms form together, layered on top of a documented, quantified stress increase on a fault capable of producing an earthquake felt across the entire state, sitting directly beside an active volcanic system that requires its own separate category of monitoring entirely. That's an unusual, genuinely rare combination of overlapping geological hazards concentrated into one relatively small stretch of California desert, and the accelerating pace of swarm activity there since 2019 gives scientists a legitimate, evidence-based reason to keep watching it more closely than a typical earthquake-prone region might otherwise warrant. None of that means a major earthquake on the Garlock Fault or anywhere else in this region is imminent. The scientific consensus remains clear that swarms like these 3 don't function as reliable predictors of a specific, larger earthquake to come. But not a predictor, and not worth paying attention to, are 2 different things entirely. In this particular corner of California, still visibly working through the stress redistribution from an earthquake 7 years in the past, sitting on top of active magma, and resting directly beside a fault capable of an 8, is exactly the kind of place where continued close monitoring earns its keep. For anyone living in or near the communities scattered across this stretch of desert, the practical takeaway isn't panic. It's the same baseline earthquake preparedness that applies across essentially all of California, just with a slightly sharper edge given what's been happening here specifically. Having a household emergency plan, knowing evacuation routes independent of any single road that could be damaged or blocked, and keeping basic emergency supplies on hand are all standard recommendations that apply regardless of whether this summer's swarm manufacture fear over 3 moderate earthquake clusters. It's to explain clearly why scientists keep such close watch over a stretch of desert most people will never visit, and why that attention is grounded in real, quantified, ongoing research rather than speculation. We'll keep tracking this region as the summer's pattern of swarm activity continues to develop, along with any updates on the Garlock Fault's evolving stress state, as researchers refine their understanding of exactly how close that fault may be to its own eventual rupture. If you want to know the moment this pattern changes in any meaningful way, make sure you're subscribed, because a fault that stayed silent for the entire modern seismic record just started moving 7 years ago, and the ground around it clearly hasn't stopped talking since.